Let's continue with coupling spatial and ocular coding in V1. We have outlined these conceptual steps for stereo coding, coupling space and ocular dimensions. The filters for the summation and difference channels are used to construct filters for the left eye input and right eye input for each encoding neurons. The gains G plus and G minus, they come from these contrast sensitivity curves. So for each band, let's say this band determined by the center frequency K for the band, as in these cosine waves, will give you the summation channel gain and the difference channel gain according to these contrast sensitivity curves. We notice that the gain curve for the difference channel is not quite like the low-pass filter in the chromatic channels that we took our intuition from. In color coding, the chromatic channel, which is analogous to the difference channel here, they have their higher sensitivities much higher than the luminance channel at low frequency, but at higher frequency, the luminance channel dominates, and the luminance channel is analogous to our summation channel here. However, here, although the summation channel does have higher gain in this frequency region, when the frequency becomes even higher, the gains for the two channels, summation and difference channels, in fact converge. This is because the signal power in the summation and difference channels look like this. The difference channel is much weaker in the low spatial frequency region, but the two channels become more and more similar in their signal powers as the frequency becomes larger. And this is quite unlike in color coding, where the chromatic channels are always weaker statistically than the luminance channel in all frequency bands. For the stereo coding, this convergence of the signal powers is caused by smaller and smaller ocular correlation between the left eye and right eye signals as the Fourier frequency becomes higher. This is because the two retinal images, one image for the left eye, another image for the right eye, they are very correlated if you look at them at a coarse scale. And coarse scale corresponds to a low spatial frequency. However, at high spatial frequency, which means fine scale, they are not so correlated. For example, at these exact pixel locations, they are not so correlated. Yeah? And so if the signals in the two eyes are not correlated, then the summation and difference between these two uncorrelated signals will have very similar signal power statistically. That means when you average the summation or difference over many different stereo image pairs. Now let's see how these summation and difference Gabor filters enable us to construct the filters for the left eye and right eye, which should have their amplitude GL and GR and phase phi L and phi R. Let's introduce a vector notation to understand this construction. The important parameters in each of these filters, for example, the K plus filter, are amplitude and phase, and we can represent it by a vector. The length of this vector is the amplitude. The direction represents phase. So if the phase is 0 degree, it will be horizontal pointing to the right in this example. And if the phase is other angles from 0 to 360 degrees, then this vector's direction will rotate counterclockwise for a whole cycle. Now let's say this is the difference filter with this amplitude and that phase direction. Now let's look at this example, O2. Okay, that just means we take the second choice in these signs with the filter for the left eye as the result of K plus minus K minus. That means the difference between them. And the filter, Gabor filter for the right eye is K plus plus K minus, the summation between them. So therefore, K plus and K minus adding together should give us the filter for the right eye with this amplitude and phase direction. To get the filter for the left eye, we need the negative of the K minus filter, and this is the one. Same amplitude as that one, except in the opposite phase direction. So adding these two together, we get this Gabor filter for the left eye's input with this amplitude and phase direction. And this whole constructing method can be also understood by shifting these two vectors here so that the right eye filter comes from the K plus turning towards K minus, and that's the end result, while the left eye filter is K plus turning this way, get the final result. We can easily see that for the neural output node O1, it will be the same thing, except that this vector will be for the left eye and this for the right eye. You can convince yourself that this vector construction method is correct mathematically. It could also be used analogously for constructing the reciprocal field filters for red and green inputs, starting from the reciprocal field filters for luminance and chromatic signals. We introduce it here to make it easier for us to understand something that's more relevant for stereo vision. And that is a neuron's preferred binocular disparity. It is determined by the phases of the filters to the two eyes, as well as the wavelength of the Gabor filters. With this phase to the right eye and this phase to the left eye, then the preferred phase disparity is this one. And with this preferred phase disparity, when it's scaled by the wavelength of the Gabor filter, is then the preferred binocular disparity of the neuron. We can see that this phase disparity is determined by this phase disparity between the summation filter and the difference filter, as well as their amplitudes. This is the dependence expressed in a formula, and here also in formula is how these amplitudes for the left and right eye filters should depend on these amplitudes and phases.